Good morning and welcome to this lecture on MIMO detection. So my name is Eric Larsson and I'll be teaching this lecture. I also have with me here today two of my grad students, Antonis Pitarokilis and Christopher Molén, who are going to help me out along the way and perhaps also ask some questions. Now the purpose of this lecture is to explain some basic ideas behind some of the popular methods that are around for MIMO detection. And the target audience is graduate students and engineers who don't necessarily need to have any prior knowledge of the topic. However, the audience should be familiar with probability theory, basic linear algebra, preferably also have taken a basic course in digital communications. Now, I'd like to stress that this lecture is going to be an exposition of basic principles, not a survey of literature, because MIMO detection is a huge field, and I'm only going to cover some basic principles here that lie behind some of the popular methods that you'll find in the literature. The model that we are going to work with throughout this lecture is the following. We have a vector of symbols S1 through Sn, so there are n of them. We stack all these symbols together into vector S, and this vector S is transmitted over a channel. And this channel is described by a matrix H, which has m rows and n columns. And this way, we observe a vector y of samples, m samples, so y1 through ym. And this vector y here of samples is equal to this channel matrix H times the transmitted vector of symbols S. In addition, the observed vector y here is also contaminated by additive noise that we collect in the vector E. Now, the symbols that are transmitted, so S1 through Sn here, those all come from a constellation, from an alphabet. And this alphabet we'll call calligraphic S this way. This is a model that arises in many applications. The most important one, and also the motivation behind this lecture, is MIMO, multiple input, multiple output, multi-antenna wireless systems. And in a MIMO setup, the symbols S1 through Sn here are transmitted simultaneously through n transmitter antennas. And then at the receiver, samples are observed, one at each receiving antenna. So if we have m receiving antennas, then we'll see samples y1 through ym. And the channel matrix H here then describes the channel gain between each possible pair of a transmitter antenna and a receiver antenna. The same model is also useful to describe channels that introduce intersymbol interference. The same model can be used to model crosstalk in cables and also some other situations. So the problem of interest is that we observe this vector y and we would like to draw conclusions on the transmitted vector S. Typically, each one of the elements in this vector S, so these symbols sk here, each such symbol depends on a number of bits. And we're going to call these bits BIK. So for symbol K, the bits are BI for that K then. Usually the ultimate goal of MIMO detection is to make inference on the individual bits BIK. And specifically, that entails computing something called soft decisions. More specifically, we define a soft decision on the bit IK, and we call it lambda IK here, to be the ratio of the posterior probability that the I, kth bit is equal to 1, given that we have observed the data, and the probability that the corresponding bit is a 0, given that we have observed the data. And this probability ratio, by the way, is usually called a likelihood ratio or a posterior likelihood ratio, because everything here is conditioned on the observations in Y. All right, so this posterior likelihood ratio now can be further written in the following form. So by marginalizing over S, by summing here over all S, vectors S, for which the I, kth bit is equal to 1, in the numerator, and similarly summing in the denominator over all vectors S for which the I, kth bit is equal to 0, P of S given Y, we obtain this expression here. This expression in turn can be written as follows. By using Bayes' rule, we can rewrite P of S given Y as P of Y given S times P of S. And of course here there is also division by P of Y, but the division by P of Y appears both in the numerator and in the denominator, so it cancels out. Alright, so let's now consider the special case that all the symbol vectors S are equally likely. Then P of S here is just a constant. And the same constant appears in the numerator and in the denominator, so it'll cancel out. And let's also now consider from now on the case that the noise is additive, white, and Gaussian. Then P of Y given S here takes the form of just the exponential, or minus 1 over sigma. Sigma is the variance of the noise. Times the Euclidean distance squared between y and h times s. And of course there's also a constant here that appears in front of the exponential that contains pi and which depends on the sigma, where the same constant will appear both in the numerator and the denominator, and therefore it will cancel out. Alright, so in principle MIMO detection, or optimum MIMO detection, is no harder than this. The problem, of course, is that computing this expression here in practice is computationally very heavy. And to do it in a practical application, we will need to do approximations. And so there's always a trade-off between the accuracy of an approximation that you make and the computational effort associated with computing that approximation. All right. So one very popular approximation that you'll find heavily used in the literature is something called max log. The max log approximation entails simply replacing the summation here over all the symbol vectors, for which a particular bit is either 1 in the numerator or 0 in the denominator, replacing that summation with a maximization operator. So substantially, what the max log does is that it retains only the largest term inside each one of the sums. To compute the max log approximation, of course, we have to find, for each sum here, we have to find which term that is the largest. And the problem of finding the largest term is equivalent to finding the vector S with its elements from the constellation, the calligraphic S, that makes this Euclidean distance here as small as possible. All right, there are also better approximations than the max log. Of course, if, in the process of looking for this minimum here, we encounter some candidates, then, well, we could just simply include those candidates in the summation here. So not just including the largest term, but including the terms that we happen to encounter on the way when we are looking for the largest term. All right, so are there any questions on this?
I got one question.
Yes.
So in the likelihood ratio on the second line, shouldn't there be a square on the sigma?
Oh, all right, so you mean the sigma that appears here inside the exponential? Yes. This one?
Yeah.
Right, so this is just the convention, I used sigma to denote the variance of the noise. Sometimes, people use sigma square instead. It doesn't make a big difference. Just use sigma here to make it easier to say.
I see.
Right. All right, so we'll proceed. All right, a couple of remarks on the problem that we have just formulated. The complexity of computing optimal soft decisions brute force is of the order magnitude or cardinality of the constellation taken to the nth power. This can easily become a very large number. For example, suppose n is equal to 8 and the constellation has 16 elements, think of 16 quam or something like that, then cardinality of S taken to the nth power is greater than 1 billion. And of course this problem has to be done for every single vector, solved for every single vector received, right? So complexity can be huge. And approximating the optimal soft decision problem by taking hard decisions and then using max log doesn't necessarily simplify the problem a lot in terms of computational complexity. In fact, it's known that even the hard decision problem is NP complete or NP hard. So, all right, again, remember that this calculation that we're talking about here has to be done in real time. You know, if you implement a communication system, then you can't really save your received vectors y to a memory and then, you know, wait for hours for the calculation to finish, right? It has to be done in real time. And the problem we're talking about here is to be solved not only for each received vector y, but actually for each one of the information bits that are transmitted. And the calculation has to be implemented in power-efficient hardware. And that means particularly that we have to be careful of using too much of heavy matrix algebra. And typically, an implementation of hardware would also be done in fixed-point arithmetics. In addition, when we're looking now for solutions or approximations, we would preferably like to have a solution that has a parallel structure. So that instead of, you know, if you think of in terms of programming in computer, you'd like, instead of having nested for loops, you'd like to have many programs that can just run in parallel, that take their own in data and deliver their own output data, and then at the end you just fuse the result together. Because parallel hardware is just so much more power efficient than hardware that needs to execute programs sequentially. All right, so this problem, and particularly the hard decision problem, is substantially an optimization problem that has been studied in mathematical and optimization theory for decades. And there are methods, you know, of course, brute force search will always give the right answer, right? But there are methods that are more efficient than brute force and that have been well known for a long time. What makes the problem different in the context of communications theory is that, you know, in contrast to mathematics, we are really not necessarily interested in having an algorithm that always succeeds in finding the solution or computing the optimum value. We are happy, typically as engineers, communications engineers, if we can find a suboptimum algorithm that finds an approximation which is good enough in the vast majority of the cases and which does the job quickly. Okay. All right, so we're now going to focus on the hard decision problem. So the hard decision problem, remember, is to find the vector S with elements in the permissible constellation, the calligraphic S here, which minimizes the squared Euclidean distance between y and h times S, where y is the vector of observations and it had length m. And for simplicity of exposition here, I'm going to assume that everything is real valued, okay? So y is in Rm, and h is the channel matrix, which had dimension m by n. Now, the constraint here that the symbols sk belong to this constellation is often of the type that, you know, sk is equal to -3, -1, +1, or +3. That would be like a scaled 4-PAM constellation or so. And typically, m is at least as large as n, so that we have at least as many, you know, think of the MIMO context, and we have at least as many receiving antennas as we have transmit antennas. And also typically, and that's an assumption we're going to make here, the matrix H is full rank, so it has full column rank, and it has no particular structure. If H had structure, for example, if H were tuplets or block tuplets or something like that, then there are different classes of algorithms that I'm not going to touch here in this lecture that could be used. So the assumption here is that H has no particular structure. All right. So the first thing we're going to use here is that we're going to decompose H by using something called the QL decomposition. So we'll be writing H as a product of Q times L, where Q is m by n. So Q is a tall matrix, and L is n by n. So L is a square matrix. And where Q is semi-unitary, so that all its columns are mutually orthonormal, so Q transpose Q is equal to I, and where L is a lower triangular matrix. Everything that L has above its diagonal are just zeros. Now, this QL decomposition is substantially equivalent to the QR decomposition that I'm sure you're familiar with. The reason I use QL instead of QR is just that some of the math that follows will be slightly simpler if I use the QL instead. All right, so with this decomposition, we can rewrite the objective function of our optimization problem in the following way. So consider now this squared Euclidean norm, y minus hs, norm squared. if I write this squared norm as a